Welcome. We're very happy this week to have Robert McGehee here from University of Michigan. Rob got his what was an undergrad at Cornell before going to Berkeley for graduate school and getting his PhD with Hitoshi Murayama, and now is a Lineweber Fellow at UMichigan, and will be telling us about some cool dark matter stuff. So, Rob,
awesome, cool. So thanks a lot for having me. It's fantastic to be back in person places and chatting with folks about fun things. So today I'm going to tell you about hopefully what you'll find interesting stuff that I've been doing with Gilly and Aaron for the last little bit, it's dealing with trying to get the maximized direct detection with a wonky new dark matter acronym that we call HYPER. So since we're going to be talking about direct detection, let's see, you go?
You might have to click in the window.
Oh, the meeting is being recorded by the host or participant.
Oh.
Got it. Okay. Good. Thanks for that, Zoom. All right, very good. Now let's see. There we go. Okay. So since we're going to be talking about direct detection, I figured I'd give you a nice cartoon refresher to wake us up after lunch, wake myself up too. So the idea with direct detection, of course, is you're going to try to directly detect dark matter, right? So dark matter chi comes in, scatters off some standard model target. Here I've drawn a nucleus, could also be an electron, and then it goes off on its merry way. And the whole purpose is to hopefully try to see that nucleus or electron in some cases get a kick. And you do this in your nice, huge, big, sensitive WIMP detectors, like the Xenon experiment pictured here, which is like insanely massive. It's 3 stories tall. It's super impressive, and here's people for scale. So very cool. So you go and you look for these super rare nuclear recoils, and you try to find them. And of course, unfortunately, so far we haven't found them yet. Otherwise, I'd be giving a very different talk about WIMPs within the MSSM and whatever, measuring all the various parameters there. But we haven't found them yet. And so instead, what these huge, impressive experiments do is they set very stringent bounds on the dark matter nucleus cross-section, right? So at present, you've probably seen this plot a million times. We're looking at cross-sections smaller than 10 to the minus 46 centimeters squared at tens of GeV sorts of masses. And this is the state of the art, right? So an obvious question is, this is where direct detection is right now. What's the future of direct detection? And some simple answers that you can give, although they're maybe challenging to actually implement, is to just go off in different directions from this plot, right? So perhaps maybe the most obvious idea is to try to go lower, right? By which I mean just try to explore even smaller cross sections, right? All the way down to the neutrino floor. And this is arguably the most challenging direction. This is what all of these large collaborations are attempting to do by building ever bigger detectors, right? And reducing their backgrounds ever more and more. And it's even this business where these different collaborations even have to merge together to make it bigger, right? So like Lux is no longer a thing, it's part of LZ, and the L in LZ is for Lux. And so anyways, these guys are building bigger and bigger stuff to try to go in this difficult direction of going lower. So I won't talk about this direction at all today because I'm a theorist and I don't know how to do hard things. And so instead I'll talk about these other 2 directions, which I'll hopefully convince you are interesting, going lighter and going higher. And so first of all, the going higher is a little bit of a tease because of course, if I just go up a little bit in cross section from what I've drawn here, you'd say that that's ruled out. So I don't have in mind going higher directly. What I really mean is going higher and going lighter simultaneously, okay? So there's a group of ideas that have been thought about in the last few years with how you might try to probe much larger cross sections, but still at much lighter masses, so sub-GeV dark matter, from what I just showed you. And these all go under the umbrella term of sort of cosmic ray scattering or cosmic ray upscattering or something like this. And the brief idea here that we'd like to know is just if you have some sub-GeV dark matter, okay, then you don't have enough kinetic energy typically when you come into these large direct detection experiments to kick a nucleus hard enough above threshold. And so normally you'd say, okay, it's game over. And actually then you're in this scenario over here where the sensitivity is just spiking up quickly because your Boltzmann distribution is you're picking up the tail of your velocity distribution, and eventually you can't see it at all. But instead, what you could imagine is that if you have way huge cross sections, so bigger than order 10 to the minus 30 centimeters squared, which is something like 16 orders of magnitude larger than the smallest sensitivity I just showed you for the xenon plot, then what you might have happen is you might have your dark matter get kicked by cosmic rays. It'll get boosted like crazy, have a ton more energy than you naively expected, and then if it has a very large cross section, it might not only get kicked, but also then go into your detector and kick something in there with way more energy than you thought. So this is the sort of idea in these cosmic ray upscattering papers, and you can see that people have looked at placing bounds both using typical dark matter direct detection as well as neutrino experiments, because you can really have a lot of energy from these cosmic rays. But the first question I want to ask and address today, hopefully, is dark matter here? Is there really some compelling story of the dark matter origins, which puts dark matter at sub-GeV masses with arguably quite large cross sections to nuclei? So that's the first question that I want to address in that sort of going higher direction that I mentioned a few slides ago. And the other direction that I want to address today is going lighter just generically. So not necessarily to absurdly large cross sections, but just generically considering what people have been thinking about when they talk about probing lighter dark matter coupled to nucleons. So the difficulty here is that your recoil energy can scale like dark matter mass squared, or the mass of your typical nucleus. And so that gets really hard in xenon with this big massive nucleus. It gets really hard to make sufficient recoil energies when you go to lighter sub-GeV dark matter masses. So one way that you might try to get around this is you might try to have a lighter nucleus, for instance. So one of the proposals for sub-GeV dark matter scattering experiments, direct detection experiments, is to use superfluid helium. So helium's a lot lighter than xenon, obviously. And I just want to point out sort of the ballpark numbers in the parameter space here. So we're thinking about sub-GeV dark matter, okay? And we're thinking about actually like not absurdly tiny, absurdly large cross sections. This is like 10 to the minus 43 centimeters squared if they had like a kilogram here of some superfluid helium. And so, these are not quite as sensitive as, the state-of-the-art xenon experiment, but these are also not incredibly large cross sections. So people are hopeful to maybe probe sub-GeV dark matter coupled to nucleons using this superfluid helium. And this isn't the only direction that's been proposed over the last, 5-10 years. There's actually been a number of directions. So just to rattle them off without going into any specifics whatsoever, there's been ideas about using color center production in crystals, also sub-GeV down at cross sections similar to helium, molecular excitations against sub-GeV, slightly higher cross sections, but still very interesting. Using multiple channels and all sorts of different materials. So here are materials that have names that I don't know. Okay, cool. And then let's see, what else? Silicon carbide, diamond again with multiphonons, and then another chemical compound that I have no idea what its name is. So the picture that I want to paint for you here is just that there's been a lot of work. This is a very active area of work. A lot of theorists have been thinking about this, and experimentalists. And people have been learning condensed matter for the first time, and it's all exciting and fun. And not that that's a bad thing. I don't, it's fun. So
no judgment.
No judgment at all. It's true, right? Like a lot of theorists have been learning. It's fun. It's good stuff. It's a good, So anyway, so a lot of people have been working along this direction. And the second question that I want to answer today is where's the dark matter, right? So in all these sensitivity plots that I showed you, there's not like one curve here that says like, oh, here's a simple model of dark matter that puts me, right here, boom, let's go look for it. That's not to say that there don't exist models here. There are some, but there's not many. Like there's only a few that I kind of have in mind. So this is the second question that I want to answer today. Okay. Good. Okay. So I mentioned two questions that are really going to be the entire focus of my talk. So the first question that I mentioned is dark matter here?
Yes, it is.
Huh? Yeah, it is? Oh, okay. We'll see. Yeah. Well, so is dark matter here specifically in those large cross sections, right? And so I'm going to actually sort of grow that question up. It's going to mature for us very quickly. And the real question that I want to ask and answer is, what is the max cross section of sub-GeV dark matter scattering off nucleons? Okay, so that's the first question that I want to answer. That'll be a slightly easier question in some sense. The second question that I asked about just generically, where is dark matter that's sub-GeV coupled to nucleons with these sorts of cross sections that are going to be probed, hopefully, in the next few decades or whatnot. Really, I want to answer two questions here. So first of all, like I just mentioned, I want to find out if we can come up with a dark matter candidate that lives there that's like not totally, wonky. And secondly, I kind of want to answer this maybe slightly more difficult question of, can I come up with a model that actually has like as large as possible cross sections? So that'll be a little bit more difficult. Okay, good. And it goes without saying, like, please interrupt me. Well, on Monday I claimed I don't love the sound of my own voice. I probably do. But I also love talking physics, and so please, interrupt me and tell me I'm being stupid and everything. Okay. All right, so the first question we're going to answer, maybe the slightly easier one to answer, at least with a bunch of caveats, is what's the max cross-section of sub-GeV dark matter scattering off nucleons? Okay. So how am I going to do this? I'm going to write down a really overly simplistic Lagrangian, and then I'm going to estimate what the biggest cross-section for this very simple picture is, this toy model. And then I'm going to claim that, due to a little bit of robustness, this is not an unreasonable estimate of the max cross-section. Okay? So the first thing we're going to do is we're going to write down dark matter. We're going to couple it to some mediator, phi, and we're going to couple that mediator to nucleons, since that's the cross-section we want. We want it to scatter off nucleons. And then I won't say anything about its coupling to other stuff, but this is the simple thing we'll write down. Now already, there's a little bit of model dependence on where that phi n bar n comes from, okay? So just to give you an idea of where we're gonna have it come from, but I'll mention this more a little bit later, I'm imagining that we have some very heavy vector-like colored things that actually couple to phi at, say, the TeV kind of scale, and after integrating those out, I get a coupling to gluons, which after QC goes to nucleons. So this is, I'll come back to this, it'll be important in a second. But for now, we can just immediately write down what this direct detection cross-section is, okay? And I can say that, the max cross-section basically just means, oh, and I apologize, there's no 4 here, okay. There's no 4 in the paper, I apologize. It's good that I already have a mistake. I already have a mistake that I noticed, I apologize. But anyways, so, it's kind of silly and easy to say what's the max cross-section. I sort of just take the maximum couplings and I take the minimum mediator mass, and that's it. So really what we want to do is we want to understand, like, what are the constraints on these things currently. So let me start with the mediator and its coupling to nucleons. Okay, there's a few relevant constraints for this light thing. The first comes from energy loss in supernova 1987A. So if you have large enough couplings, but not too large that you would accidentally retrap produce phis, then you can have a too great energy loss mechanism in your supernova, and we wouldn't have observed the neutrinos like we did, and it's a problem. And so an order 1 sort of power from any new light degrees of freedom is ruled out. And so that rules you out up to Yukawas of order 10 to the minus 7, okay? There's a similar argument you can make with stars, and in particular horizontal branch stars. And so these, you can really rule out a much larger range of couplings, but they can't probe nearly as high mass as a mediator. So around hundreds of keV, they can bound. And finally, you can have rare meson decays that come in, and so you can have your standard model mesons decaying to stuff and these phis. This is provided for by actually the phis coupling to the top. And here's where this little detail that I said on one slide ago about the UV completion of the phis becomes relevant, because this phi n bar n coupling, where it comes from tells me like what roughly is coupling to tops is. So there's a different simple UV completion that I could have written down for this phi n bar n coupling, where I just coupled it to tops immediately, okay, and then at some higher scale above electroweak did something else. But if I had done this, then I would have provided for faster kaon decays, okay? And in that kind of UV completion, actually this entire sort of middle white area. This gray isn't really showing up, but trust me that this is gray and everywhere in the middle is white. This entire middle white area would have been totally ruled out, okay? And so then you would have to go to quite heavier phi masses before you get any viable parameter space. So already in choosing this UV completion, I've tried to pick one that gives a larger cross section, because the name of the game is how big could it be, like in any kind of realistic scenario, okay?
Where's BBN on this?
Good, no BBN yet, so good. So the only thing I'm showing here are sort of present day bounds on the mediator, and I'm not saying anything about BBN yet because we're gonna do some wonky model building. Yeah, but thanks. So the punchline of my game of estimating this maximum cross section is to only take present day bounds. So I'm only gonna take present day bounds in one form or another, and we'll try to justify that by coming up with a wonky cosmology such that you evade the usual cosmological bounds. Yeah.
Another question, you seem to always assume that your dark matter is like a fermion and your mediator is a scalar. What's about other possibilities?
Yeah, very good. So I'll talk about, let me come back to both of those in like 3 slides. If that's okay.
Sure.
Yeah. And then if I didn't answer the question, then you can yell at me and be like, you promised me. But yeah, no, it's good. For now, they're just like assumptions for no good reason. I'll try to give you better reasons in a couple slides.
So not to derail you too much, but so in the plot that you were showing us earlier from Catherine and friends, they had a similar kind of model, but this was for the purpose of showing the scattering off of helium. And there they didn't show the BBN bound. So was there, because presumably they weren't making some sort of claim about cosmology.
Yeah, let me see what they were doing. I forget. Let's see. So here, let's zoom in. Yeah, so here they don't have a BBN thing. Yeah.
I mean, it's not far off from where the big wall hits you, but I would expect it to be there.
Yeah, that's right. So
you're not obligated to defend someone else's paper.
No. So yeah, let me think. Yeah, it's a little odd because of course also in their various papers they'll vary, what fraction of dark matter it is and get around stuff sometimes that way.
But
this is one, but
that wouldn't matter because if you tell me there's a 500 keV mediator and it has a coupling sufficient to give you that cross section, it'll be thermalized, and so now you've got some extra stuff pushing the universe to expand.
Yeah, that's a good point. Yeah, why did they not do? Yeah, I would just have to say that maybe they were just being agnostic about the cosmology as well. In our case, I'll try to justify it, of course, because I'm gonna do the whole thing, but I'm not entirely sure. Yeah,
fair enough.
Yeah,
they're not here to defend themselves.
Yeah, I'm sure they had good reasons, or they very possibly just say it in the paper, but I do not recall what exact words they use. Okay, good. Yeah, please keep interrupting because then I can drink coffee. Okay, good. So all right, so if you accept these few words that I said and these few constraints that I showed you, then we can just quickly read off what sort of the minimum mediator mass roughly is at the sort of 0.3 MeV level, and what kind of the largest coupling is to nucleons at the like 10 to the minus 5 level. So then we only have one more chore remaining. We need to know like what the maximum coupling to dark matter is. And for that, again, just to re-emphasize because of Gordon's good question, I'm only going to take present day bounds. So here for dark matter, I'm just going to take present day bounds on the dark matter self interactions. So this is just a nice, pretty plot. It's not super relevant for us, but I like to show it. It's hints at maybe what dark matter self interactions might be. So on the Y here, we've got sigma V dark matter self-scattering per unit mass of dark matter, and on the X we have as a function of velocity, and so we see over a whole bunch of different scales from like dwarf galaxies, low surface brightness, SIDM simulations, and galaxy cluster data at the highest velocities. We see that there might be some indication that dark matter might have some self-interactions. Okay, so this is just a pretty picture. For our purposes, we're going to take the typical bound that's maybe pedagogical at this point. This is the sort of usual bound that people hold themselves to, model builders at least, which is that we require dark matter self-scatters per unit mass to be less than about a centimeter squared per gram at something like 10 to the minus 3 velocities, okay? And so in order to solve for that maximum y-chi coupling, we're just gonna saturate this bound everywhere. So y-chi max turns out to be like roughly 10 to the minus 2-ish. It's a little bit mass dependent, but anyway, somewhere thereabouts. Okay, so now I can just immediately tell you what our maximum cross-section is now that I've so strongly convinced you about our various parameters and their extrema. So, okay, so we're thinking about dark matter masses between roughly pion mass down to 50-ish keV or so. I'll motivate that choice in a little bit. And then we're thinking again about the dark matter scattering off nucleons. And so here's our maximum. So at like pion masses, it's something like 10 to the minus 30 centimeters squared. And as you go down, by the time you get to like 10 keV-ish, it's like 10 to the minus 36-ish centimeters squared, okay? So I'll point out two things. The first thing is that I've also shown in dashed gray here a variety of these different sort of sensitivity projections for all of these very future experiments. And so the first thing to note is that it's nice that the sort of maximum, quote unquote, that I've estimated here is like many orders of magnitude above the sensitivity of all of these experiments. So that's like a nice sanity check for those experiments. The other thing that I'll note is that this is not an absurdly large cross section, and it's certainly less than 10 to the minus 30 centimeters squared. Okay, so let me now get back to your question a little bit, and then you can ask again if I don't address it. So what's the robustness of this estimate? Okay, so the first thing that I'll claim is that we tried to choose a UV completion for the phi nucleon coupling, which resulted in the largest cross section. At least we did our best effort. And I had already mentioned that if you coupled the tops directly to generate your phi nucleon coupling, then your meson bounds are going to be even stronger, and so that's going to make a much worse cross section. You can also consider coupling to light quartz, but there again, just naively, you'd expect these meson bounds to really be an issue, and you might have to push the mediator mass again past say GeV scale. Which compared to our 0.3 MeV thing is substantially worse in terms of cross-section. And then, okay, you could ask, okay, but what if you don't use a scalar mediator? What if you use a vector mediator, right? So we considered this possibility for a few obvious choices. So we looked at visibly decaying dark photons, invisibly decaying dark photons, U1b minus L, and U1b, anomalous, okay, and maybe just assuming some crazy UV completion. And in all of those cases, the cross-section that you get from imposing present-day bounds is just smaller. In some of those cases, like B minus L, it's like many orders of magnitude smaller. In some cases, like invisibly decaying dark photons, it's around the same sort of size that I showed you for the scalar case. So we just sort of went through the laundry list and checked. There's no deep reason. Well, one sort of deep reason is all the things that I just mentioned also coupled to leptons, and those things happen to give you strong bounds when you go to light masses. But anyways, there was no profound reason to choose the scalar to begin with, and we kind of just went the whole laundry list and tried to choose one that would give the biggest cross-section. Good.
How about if you assume that your dark matter couples only to, say, leptons, like electron, rather than the quarks and gluons?
Yeah, good. So if you only couple to electrons, then you don't generate a dark matter model for the parameter space I'm interested in. So specifically, I really want to focus on the scattering off nucleons dark matter. One of the reasons is because when you have light dark matter scattering off electrons, there do actually exist compelling benchmarks. So there are freezing curves there are dark photon freezing curves, which are viable and give actually interesting benchmarks for these sub-GeV dark matter electron scattering experiments like Sensei. There's even a freeze-out curve for heavier dark matter masses in that case. So there's a lot of simple models that I can point to, and so yeah. So you could 100% do that, and but anyways, that was not the first thing we did because good. All right. Good. So now let me point out a couple caveats, all right, to this estimate of the largest cross section. The first is that those meson decay constraints were really important. So the updated Na62 measurement from a year ago fed directly into what I ended up assuming for my maximum Yn, okay? This came entirely from the sort of loop-induced coupling to the tops though of phi TT bar, okay? And so if you have some fine tuning in your phi TT bar coupling, so you not only have sort of your phi glue, but you also introduce a phi TT bar such that you can try to start canceling off this contribution to the meson decays, then you can play, you can play a game where you actually alleviate the meson decays, okay? So that is one caveat. We didn't permit ourselves fine tuning when we estimated the maximum cross section, but if you had a cool model or a good reason to cancel off the top sort of coupling, then you could get larger. And the other caveat that I know of that certainly has larger cross sections is large composite states. So if you have asymmetric dark matter and you build up mounds and mounds of order, say 100 sort of particle dark matter all bound together or even larger, then you can get larger cross sections for sure. Obviously, my very simple toy model estimate knows nothing about large composite states. It just had like one particle dark matter scattering via one mediator. And so anyways, this is one way that I know of that you can get larger things. Okay, good. So with all those caveats and claims of robustness in quotes, I can try to sort of answer this question: is dark matter here for these sort of larger cross sections at sub-GeV? And I think the answer is probably not. And I'll just point you to Gordon and Sam's other paper where they looked at sort of complementary reasons that you might think a lot of this parameter space is ruled out for BBN reasons alone. Okay, so probably not. All right, there are caveats. You could have large composite states that could be up there. I haven't proven anything, but I'm just, these are just silly ideas. But my claim is that it's probably not there. And you might say, okay, so what? So it's not there. Tell me something new. Dark matter is not somewhere we looked, right? This is our whole life right now. It's not there. Okay, so what? And I'll just point out that it's relevant to know what models you're looking for, right? Which is also why we're trying to build models for these new detectors. And so it's just relevant for folks to know what kinds of models are at those large cross sections. And so there have been a couple of good, very robust recent analyses by these large experimental collaborations looking for this cosmic ray upscatter dark matter. And it's just relevant to know what models you're actually looking for. Okay, so I'll just say, it could be a good thing to know.
So can you remind me what prospect is? The prospect bound they are coming from?
That I don't know off the top of my head. Yes, that I'm not super sure. Let me.
Yeah, me neither. That's what I'm saying.
Yeah, sorry. Let me look at that offline and.
Right, but your max cross section curve that lies mostly below. You're saying these experiments are probing places where it probably isn't.
Yeah. Good. So to scale here, like here's pion mass, and so our maximum here was let's see, for where am I at? Yeah, so for pion mass, our maximum is somewhere around 10 to the minus 30. And by the time we go down here, this is, I can't do math quickly, 100 keV. So by the time we get down here, it's like 10 to the minus 35 centimeters squared, so 3 orders of magnitude down. So there might be, a absolute sliver of overlap right here, but down here, then you're, anyways, yeah. Good. Okay. So that was perhaps the easier question to answer, at least with all these caveats, because I just did a really hand-wavy tilde estimate. So actually, the more interesting question or set of questions that I want to address for the latter chunk. And how am I doing on time? I don't even know. Wait, when did we start? Oh, 1:30. Okay, good. So the second set of questions that I now want to address, which is a little bit maybe more challenging, is like, can we actually come up with a dark matter candidate which can be detected at all of these proposed experiments that I showed you, which also might have a cross section like as big as this estimated maximum that I just showed you. And before I get to the answer, let me tell you why it should be concerning and scary to try to do any model building in this direction. So you need a light mediator. You need it to have as large couplings as possible to dark matter nuclei. What could go wrong, right? A lot of stuff could go wrong. So first of all, you could have large dark matter annihilations to phis, just generically, because our coupling is something like 10 to the minus 2, which is not absurdly small, and phis are very light. So if you have really, really large annihilations, then you could ruin your relic abundance in the early universe. Even if you don't do that, you might be worried about indirect detection bounds from CMB or present day just looking at galaxies. And then even ignoring the large coupling of dark matter to the mediator, just thinking about the mediator itself, like Gordon was saying, if you've got a mediator that is light and coupled to the standard model with a reasonable coupling, then you're going to thermalize that mediator, and then that's going to contribute to ineffective, and that's going to be a big problem at BBN and CMB. So these are all the things you should be worried about, okay? If you try to play this model building game. All right, so getting back to the questions here, I hope to convince you that the answer is this new silly acronym, okay? At least one of the possible answers. I would like to cut myself a little bit of a break here because this is one of the acronyms that actually has the meaning in the acronym a little bit. So these highly interactive dark matter candidates, they're highly interactive. So it's like, they're hyper, right? So anyways, that's my, epsilon excuse for coming up with a new stupid acronym. But anyways, you'll forgive me if I call them hypers, hopefully, for the rest of the talk. So what's the story here? Okay, here's the cosmological history of hypers. So at early times, at reheat temperatures, at some TR reheat temperature, we assumed that these hypers freeze in, and they do some UV freeze in. So all the relic abundance is immediately set, okay? And the relic abundance is only dependent on the reheat temperature and the mass of your mediator, which I have suggestively not called M phi, I've called it M phi I for a reason that we'll get to in like half a slide. But first, just to remind you about the UV freeze-in story. So for those who don't play these sorts of model building games, the black curve, this YFO, this is your usual freeze-out curve. So on the Y here, I've got my dark matter yield, which is number density per standard model bath entropy. On the X, I've got dark matter mass over temperature. So as you go to right, you go to lower temperatures later times. So the usual freeze-out story is that your dark matter starts out in thermal abundance. And then as you go past x's of 1, where it starts becoming non-relativistic, you start going down the Boltzmann tail, and at some point you exit because your annihilations can't keep up with expansion, okay? So that's the usual freeze-out. Now we're not gonna be thinking about freeze-out, we're thinking about UV freeze-in, which is one of these two oddly shaped curves here. So both the red and the blue correspond to freeze-in scenarios. This red one is called IR, and the blue one is called UV. We only care about the blue one, and the only thing that really matters for UV freeze-in is that your mediator is sufficiently heavier than your initial reheat temperature, such that you're way always out of equilibrium, and such that your rate of producing your dark matter from standard model bath annihilations is fastest at the earliest times. So you just make dark matter boom, like all right at T reheat, and then you're done forever, okay? So this is a scenario where you have really heavy mediators. Like I said, it's always out of equilibrium, and the rates of these annihilations are always much, much slower than Hubble. Okay. So
is it important for your story that it be symmetric? Could you have it be frozen in with a matter asymmetry in the dark sector?
I don't think that it's important that it's symmetric. If anything, it'll probably make our story easier. Because so we just assume symmetric, but if you have some way to make it asymmetric, then actually the most problematic process that I'm going to get to in a few slides is dark matter annihilations after the phase transition that I haven't introduced yet. And so asymmetric could help you actually a ton. Yeah. That could be a fun model building direction to go along, which we have not. Okay, good. So how does UV freeze-in work out in our story? So as I already said, we have some heavy vector-like colored things coupled to phi, which generates phi's coupling to gluons. But we're going to assume for now that we have a really heavy phi relative to the T reheat temperature. And so we integrate out phi, and we're left with this dimension 7 coupling between dark matter and gluons. And this higher dimensional operator is what is responsible for the UV freeze-in of these hypers at the reheat temperature. And just to give you some idea, we're looking at sort of like tens of GeV to hundreds of GeV. we won't be able to get a story, at least not with a maximum cross-section at the TeV scale, because for instance, that's where we put our vector-like colored fermions, okay? All right, so what's the next step in the story after freeze-in? After freeze-in is where the wonkiness kinds of enters into our model building game. So we're gonna assume that there's a phase transition in the dark sector at a later temperature, later time, TPT, which causes this initial mediator mass, which I suggestively put a little I here, to decrease substantially, okay, to our final present day M5. It's gonna drop like crazy, and I'll just point out a few interesting papers that considered some other interesting uses of dark phase transitions, changing masses and such. The reason we're gonna drop the mass like crazy, and we want to, is because the direct detection rate goes like 1/m⁴, at least in the heavy mediator regime. And so if you play this dropping mass game at late times, you can boost your present day direct detection signal by m/m⁴. Okay, so this is how we can try to get a really big cross section. And again, I'll just point you to another fun paper that considered changing present day interaction rates. So there should be some red flags going off immediately in your head, right? So I told you all these difficulties with model building. I sort of stalled all those difficulties at early times by having a really heavy mediator, but the second that I dropped the mass of the mediator, all of these problems could reappear, right? So I could mess up my relic abundance, I could mess up BBN somehow, contribute to ineffective, I could mess up CMB, indirect detection, blah, 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 blah. Everything could be terrible. So my job is to try to convince you that we can take care of these red flags. Okay, so first of all, changes to relic abundance. What might be we be worried about, okay? So after the phase transition, dark matter is coupled to hadrons, so you might be worried about dark matter annihilating to hadrons once that mediator becomes really light. So we can try to do away with this by making dark matter sufficiently light, so lighter than pions, and by having a sufficiently low phase transition temperature. So if dark matter is light and phase transition is low, then I can't annihilate to hadrons. But the opposite is also true. So if the phase transition is really quite lower than the pion mass, there are no hadrons in the standard model bath anymore to produce my dark matter, so I can get rid of both directions of that potentially problematic process. And hopefully, if I take a low enough phase transition temperature, then the loop-induced coupling of phis to photons can also hopefully still be too small to produce a problematic amount of phis or dark matter.
Are you assuming that even lighter mediator is heavier than dark matter mass, or?
No, so sometimes the mediator will be lighter than dark matter.
Then you can annihilate it to lighter mediator and to.
Yes, so we're happy, but then you asked your question, so now we're scared.
Okay.
Okay, very good, very good. Yeah. So this is entirely the problem, which is why I said the asymmetric dark. If you got a compelling way to get asymmetric dark matter, then you could really increase our parameter space probably quite a lot.
So isn't there just some literature on asymmetric freeze-in that you could use?
Potentially, yeah. I just haven't. I really haven't thought about it at all, but. Yeah, if there's some cute asymmetric freeze-in thing that we could do a similar picture with the mediator, then yeah, it could definitely make things better.
So how big is the annihilation cross-section as a figure of merit?
How
Like
big
if you only cared about direct detection and then you translated those couplings into an annihilation, sigma V, would it be like bigger than the nominal thermal cross-section for this stuff?
Well, so I guess my only intuition that I have is I know how big the rates are at MeV scales. That's sort of my going benchmark. And so I know that for most masses, the rates are fast relative to Hubble at MeV temperatures. Yeah, because that's going to be the thing that we have to fix. Okay, good. So this annihilation process that I told you a few slides ago can be a real problem, okay? It's a real challenge, and we can't make a smart kinematic choice about, we assume this about the mass of dark matter or the phase transition temperature to get rid of it. So this is actually going to be a problem for us. And as we'll see, for some parts of our parameter space in light dark matter, we can't actually get all the way up to this maximum cross-section that I told you about for this reason. Okay, so let me show you a pretty plot. So here's that figure I showed you a few slides back. Here's our maximum cross-section, and we're trying to do a model building game to get as close to that cross-section as possible, okay? Here's the result. So you'll forgive me for calling this hyperspace, I couldn't pass it up. So everywhere in blue here, I claim that I have a consistent cosmological history of dark matter that explains the relic abundance, even if it's wonky, and explains the present day direct detection signal. So there it is, okay? So let me try to
Sorry,
yeah,
you
good.
said this, but I forgot it. Exactly what are the ingredients in the sigma max that you put there?
Oh, sorry, the black line?
Yeah.
Yeah, so only present day bounds. So I've got bounds on the mediator mass and coupling to nucleons coming from, really it's kaon decays, so it's k to pi phi bounds the nucleon, the Yukawa of the phi to the nucleons. And the lower bound on the mass is coming from horizontal branch stars. So that makes you have mediators heavier than 0.3-ish MeV. Those are the two that matter. And then for the coupling of the mediator to dark matter, I'm just taking dark matter self interactions to be a centimeter squared per gram.
Yeah, that's what.
At 10 to the minus 3 velocities. Yeah.
So, does it matter that the annihilation cross section is P wave?
Very good, thank you. So that's 2 slides. Good. So okay. So here's the answer to your question. Yeah, it matters. So it's great. So let me try to give a little bit of intuition about the various like sort of slices on the top of this region here. So we tried to get the largest cross section possible. So everywhere here, we're choosing M phi and Y chi to try to get the largest cross section, and we're setting Y in just to be that maximum allowed value. Okay, that 10 to the minus 5 that I showed you. So this first part over here, for masses heavier than roughly like 17 MeV, you'll notice that we actually managed to get hypers that have cross sections as big as this maximum. How do we do that? Because I told you that these chi-chi to phi-phis are a problem. The answer is that it's p-wave suppressed. So this parameter space here, I'm assuming my phase transition is 1 MeV, and if I have a 30 MeV dark matter, it's going to be quite cool by 1 MeV. And so this p-wave suppression is going to be sufficient to make this rate slow enough. Okay.
What stops you from considering much higher reheat temperature and then just expand this blue hyperspace?
Good. So a few more slides. But the punchline though is that as you go to higher phase transition temperatures, more and more standard model processes are trying to make phis and chis, and it gets harder and harder to have a large cross section. So I'll show you in a couple slides what a 5 MeV phase transition looks like. And it's not abysmal, it's still detectable, but it is lower than what I'm showing here. Yeah. But yeah, there's a balance, right? So if you go to higher phase transition temperatures, you might have a less wonky looking dark sector and model, but you're gonna get a smaller cross section. So it's a trade-off.
Well, but you're assuming that at the highest temperature, you're producing both the standard model and you're only producing this through freeze-in via standard model initial states, right? Nothing's forcing you to do that. In principle, you could just have some early matter domination or some other thing, and you could do freeze-in through that, and then you could then later heat up the standard model at a much lower temperature from the decays of whatever was responsible for that. You could sort of separate those.
Oh, you mean from having to have the UV freeze-in thing?
You would still have it be UV freeze-in, it just wouldn't be freeze-in off standard model initial states. So the picture would be there would be some early matter-dominated phase of some other thing that decays, and you freeze in the dark matter at very early times, and then the standard model abundance comes in with a small enough branching fraction that its temperature is lower, that you don't have to worry about those other processes.
Oh, I see. Sure, that could be possible. But once you go above like 7-ish MeV, as I'll show, pion processes start mattering, even though they're almost gone. And so, yeah, it could, you could have fun with having a more interesting cosmology that puts you at a low effective temperature where you might be considering the phase transition. But regardless, the phase transition is already a hard game to play. So like, yeah. Okay, good. So let me try to give just some really quick intuition. How much time?
15 minutes.
15 minutes? Okay, good. Let me try to give some really quick intuition just about the various shapes here. Okay, it's not super important, but maybe it gives you an idea about how hard it is to try to model build. All right, so as we go to lighter masses, this p-wave suppression that I just mentioned in the annihilations is no longer sufficient, okay? And so at this first kink in our curve here, we're having to choose couplings that are smaller than the allowed maximum. Okay, so that explains this first downward trend here. Now we want to make the largest sigma possible. So what we found is that actually, as you go to lighter masses, it is easier and better to suppress this annihilation just by making phi heavier rather than taking the coupling smaller. So if I make the phi mass equal to the average energy of chi's at the time of the phase transition, then they just can't make phi's, and it turns out for this range of masses, this is the better way to get the large cross section. Now there's a steep drop, so there has to be a good reason. Something absurd is happening here. What's happening here is that phi's are becoming always heavy enough to decay to 2 dark matter, okay? And then inverse decays of photons, gamma gamma to phi, is producing enough phi's to mess up your dark matter relic abundance, but still too few phi's to worry about for ineffective. So I'll just point that out, just in case you're curious. But the dark matter relic abundance is harder than ineffective, as you would imagine, because 10 to the minus 9 is a small number. So anyway, so you start getting a problem with these phi's potentially decaying to dark matter. And so then what you have to do is you really have to crank up the phi mass so that you just absolutely are never producing them from photons due to Boltzmann suppression. So that's why there's a huge drop there. And finally, even at these lightest masses, not only do you have to crank up your phi mass, a factor of 10 bigger than the minimum phi mass, you also then additionally need to decrease the coupling due to annihilations of photons through this off-shell heavy phi still being a problem for producing dark matter. So it's not easy, okay? It's not an easy game, and clearly, at the lighter masses, it's really difficult to get close to this maximum cross-section. Oh, and I'll just mention one other point. The reason I've cut off here is I've cut off at dark matter masses where twice the dark matter mass is roughly the plasma frequency, because we didn't consider anything about plasmons decaying and producing dark matter. That's just beyond the scope of our first little initial paper here, and so I don't trust my estimate at lower masses. Okay, so this is a lot of effort. So what does it get us, right? So first of all, it gets us a dark matter candidate which can have this, reasonable estimate of a largest possible cross section as long as you're above 17 MeV. And even at these lighter masses, through this judicious choice of M phi being just a bit too heavy for the dark matter to paranihilate to, you can still get a quite large cross section. It's not too far away from our maximum. So that's one thing all this effort gets you, okay? The other thing it gets you is it gets you targets that at least populate all this parameter space down to quite low dark matter masses, which is hopefully going to be targeted by some subset of these proposed future direct detection experiments. So that's what all this effort gets you, okay? So now let me just say a couple super quick words. Yeah, I'll say super quick words about this, and we can talk more for people who are interested. So I mentioned this business about going to higher phase transition. What's the problem? The problem is that phi is also coupled to your pions. And so you can just start writing down all sorts of pion processes that could be making phi's and then therefore also be making chi's through either just decays of phi's or off-shell processes. So the one that we're going to focus on is just this one. It only involves one pion in the initial state, so it's not doubly Boltzmann suppressed, it's just single. And it only has 2 states in the final state. So when does this process start to matter? We can just estimate it, just requiring that its rate is sufficiently slow to not muck up the dark matter relic abundance, and we find a rough phase transition of say 7 MeV. So if your dark sector phase transition happens above the standard model bath temperature of 7 MeV, then these pion processes are also going to start kicking in and trying to make your dark matter, and then you're gonna run into problems, or you're gonna have to take those into account when you calculate your sort of largest cross section. Okay, so just to quickly show you the results, here's the hyperspace I just showed you, assuming a 1 MeV phase transition. I did extend it all the way down to 10 keV, but I dashed it because again, I have not accounted for plasmons yet, so it's just dashed. Here's what the 5 MeV temperature looks like. So as you imagine, as you can imagine, it's harder. There are higher temperatures, and so processes are faster and they're more problematic. And so we get further from this maximum cross section, but it's still very detectable, right? So even at sort of the lowest masses we can consider of, you know, a few hundred keV, we're still 2-3 orders of magnitude away from these the sensitivity of these future things. So you can still be probing interesting parameter space with these proposed future direct detection experiments.
So what prevents you from going in the other direction? Like, could you have an EV scale phase transition?
Yeah, good. So good. So if you go to lower, then there's a few things. So the first thing is then you need to maybe be extra cautious about how you have no energy or entropy dumping after the phase transition to standard model stuff. So that might be doable. There's not a hard lower limit from cosmology necessarily, but the real reason is you know, this cute thing I was telling you about, which is that a lot of these stellar and supernova bounds, well, all of them, they all assume that there's not some wonky phase transition happening in those environments. That could easily be the case if you have a very low dark sector phase transition. You could easily be inverse phase transitioning in those environments, which would impact the bounds. And this is actually a separate ongoing work with folks to understand how phase transitions could impact the usual bounds. Yeah.
2 questions. So the first question is asking again one of my previous questions. So since you're doing UV freeze in, and since you're using dimension 7 operator, naively the collision term will be like T to the 11 or something. Like,
Sorry, what will be?
so the energy injection rate will be like very high power of temperature. So that means that it depends a lot on the T reheat. That means that if you change the T reheat a little bit, you can easily either overproduce or underproduce. So my earlier question is that you can play the game that you take the slightly larger T reheat. So you start with an over reheating regime, and then you use an extra afterward dilution effect. Now you enjoy those dilution effect, and then you can see if you can get closer to the sigma max. So I believe that this is based on the fixed T reheat that you told us, I guess. And then
so T reheat doesn't impact this parameter space at all, in the sense that I have both a T reheat and an initial phi mass which is large, and I change both of those simultaneously to get the right relic abundance.
What do you mean by right relic abundance? That's not including afterward dilution effect, yes?
Not including dilution.
Yes, that's what I mean.
That's right. So if you include some amount of dilution, then what you might be having is after the phase transition, then you might say, oh, actually, I don't quite have enough dark matter. I need to make it after the phase transition, right? Is that
or I can start with the overproduction at the T reheat, and then I just dilute in proper amount by choosing like light phi mass and so on. And in that case, I have a better chance to getting closer to the T sigma max. That's what.
Well, so the boundary of this region is only determined by thinking about things after the phase transition and present day bounds. So the point of this exercise was I really set up a scenario where I totally decouple the initial abundance from what I'm seeing today as much as possible. So if you have some dilution that happens after the phase transition and it gets to the right amount, then that's okay. It means that it's the right amount after the phase transition, and I still have to worry about all this stuff.
Sure.
Because now it's after the phase transition, now I have the couplings how they are, now I have the mass of the mediator how it is, and then I still find this parameter space.
Okay, good. So
Yeah.
I think we can talk more about
Yeah,
offline.
yeah.
Second question is that presumably the mass of the phi after the phase transition, and you said that that's the way you drop the mass from the phi I to the phi. Right? Presumably then the mass of the phi, given a mass of the phi I, depends on the phase transition temperature somehow, or is it? Or did you just treat it completely free parameter, or there is a functional relationship between the mass of the little light mediator as a function of a TPT?
Yeah, so good. So it's a function of TPT only in the sense that these different regions, I'm having to make sure that none of these problematic processes are turning on. So one way that it's a function of TPT is this part of the hyperspace is determined by increasing the phi mass so that chi-chi to phi-phi can't happen.
Sure.
So that is a very T phase transition dependent statement.
But that's indirect in a sense that.
Yeah, it's
that-
indirect. It's indirect.
Right. Then do you have like a microscopic mechanism for actually how to change the mass of the mediator through the
Yeah, very
phase
good.
transition mechanism?
So I have one idea, and there's an expert in the room that I hope to maybe bother or something. So I have one hand wavy idea, which is two-step phase transitions. So these have been thought of in the context of electroweak phase transitions, where you need to juggle some maybe initially large VEV in one scale direction and reduce its spin at later times. That's the only story that I have for how you could try to drop the mass. But there's for sure going to be fine tuning because this is a huge drop in scales naively. And so whatever dark sector potential setup would give you the largest possible cross sections is going to be fine tuned. It's not going to be pretty. And so, my perspective in approaching this is really just, how close can we get to my sort of estimate? But, they're not. We did not consider anything in detail with the dark sector potential. And it's for good reason. It's because it doesn't impact the phenomenology necessarily of the direct detection, but it's also simultaneously difficult. And so this is stuff that we're thinking about if there's better ways to think about this. But yeah.
I have a related question. So would the phase transition somehow also affect the mass of the quarks, like light quark in the standard model? We induced that one loop at least, right?
What's that?
There might be some like one loop coupling of this phase transition sector to the light quark that would affect the mass at the early times.
Yeah, so that
somehow.
Yeah, so that could be possible. So in our UV completion, we have phi coupled to gluons. So yeah, you put a loop and you can get light quarks coupled to phis.
Yeah.
So yeah, that is possible. Yes.
Yeah, I would worry about the mass scale of the light quark at a very early time when you have this heavy phi.
Oh, I'm sorry. I see what you're saying. Yeah, at early times, if you it's a little bit easier because the mediator in our case is not the thing. Is not the relevant VEV scale, right? So there's potentially some other scalar that's coupled in a quartic with the phi that's giving the phi mass. Right, but phi doesn't itself necessarily have to have a large VEV at early times.
Right. So you can generate a coupling of the light quark to your phase transition sector via the loop of the.
Oh, sure. So you can have loop of phis, loop of glues, then light quarks, and then coupling to the thing that has a VEV. Yeah. That's possible. So that's something we haven't thought about. So it's gonna be. It'll be 3 loop, I guess, once you go to.
None of those loop breaks electric symmetry, so I don't think you can give a mass to the quark. Right? It's a pure Q-city or G-mu phi. None of that breaks electric symmetry.
Sorry, we have a thesis defense.
Sorry. Yeah.
Where is that?
Yeah, sorry, I'm running
Let's let
very
Rob
late.
finish
Sorry.
it.
Yeah, sorry. So
You're losing all your.
yeah. No, it's good. I don't have
audience.
anything left.
Now we can criticize professors.
Yeah. I had a small question, but I have to go because my student who is doing this. So how you define your phase transition exactly? Because it's the issue of critical nucleation, and I think it would be very fascinating to understand better how you're dealing with that.
Yeah. So we're dealing with it super naively. So the only thing that we assumed was that the phase transition is strongly first order and happens boom, and then from the phenomenology perspective, we just assume that it means you go from heavy thing to immediately light thing. But we don't have any details. So yeah, I'd be happy to chat about the.
Okay. So sorry that.
Okay, good. So we're at the end regardless, I promise. So the second question I want to answer: where's the dark matter for all these sub-GeV proposals? It might be these hyper things. Okay, there we go. So now my one final slide, future directions. We've kind of mentioned some of this stuff a little bit. So one thing that could be fun to do is to repeat this exercise for electron scattering. It's maybe not quite as motivated because there are targets, at least a couple good ones for electrons, but it's still interesting to sort of proceed with the same questions there. There, though, it gets subtle for a reason that I think I already addressed too, which is that you need a lower phase transition temperature. Then you might not only worry about the early universe cosmology bounds on such a lower phase transition temperature, but also how those phase transitions could be impacting the usual results of constraints at supernova and stellar environments. That's a direction we're exploring totally separately from this, just generically. It could also be fun to think about the sort of vector mediator case because you might just have a nicer UV completion. I think in those cases, like I mentioned, you won't quite get to this maximum cross section because the bounds are a little bit more stringent. But if you have a nicer UV completion, a nicer dark sector story, it could be worthwhile to go along those directions. And then really fleshing out the dark sector phase transition and trying to understand to what extent we could motivate without a huge amount of fine tuning some full picture of the dark sector phase transition is very much work in progress. Okay, so I answered a bunch of questions. The first question I answered was, what's the max cross section? And it's not terribly big, and I hope I convinced you that's just an interesting thing to be aware of. And the second set of questions that I answered is about how we can do some fun model building and maybe approach this maximum cross section. And the at least answer with some caveats is these hyper things. So thanks a lot. Thanks for the engagement.
Any further questions?
Other questions?
I have a question.
Yes.
How well do we understand the various late time constraints as a function of the fraction of dark matter? I have in mind, it could be the case that if you consider something that's just a tenth of all dark matter, maybe the maximum coupling you could have 100 times more or something, and then you could get a larger rate at a direct detection thinger. Good. So there's two things there. So how might you crank the story up if you have a fraction of dark matter? So if you have a fraction of dark matter, then in particular the coupling of the dark matter to the mediator can go up because the dark matter self-interactions go down. But you also pay the penalty in your direct detection because now you have only a fraction of dark matter. Right, but that's only linear.
That's linear. So it goes in the wrong way. So that is linear. That goes like 1 power of the coupling, but your self-interaction goes like 2. So when I decrease the bound on my self-interaction, I only get a square root increase in my coupling. It goes the wrong way, right? So dark matter self-interactions go like y chi to the 4th. Dark matter direct detection goes like y chi squared. If I improve the self-interaction, I only improve the 4th root of y chi, right? And I pay the price in the, anyways, I think it goes the wrong way, you know what I'm saying?
Right, I mean, unless there aren't any constraints on what, 1% of dark matter does or something.
Sure, but even then, good. So if I go down to, So if I go down to small enough 1%, say, so that there's really no self-interaction bound, then we were dealing with self-interactions of couplings of order 10 to the minus 2. So I can increase that 2 orders of magnitude, potentially, but then I get into perturbativity, so, I can't do it ad nauseum probably. But if I do 2 orders of magnitude there, and I pay 2 orders of magnitude in the number density, then maybe it comes out good for the direct detection. Because I'll go like 2 orders of magnitude in y chi, I'll get like a factor of 4 enhancement, but 4 orders of magnitude enhancement, and only 2 orders of magnitude suppression. So maybe I win by 100. If I have a subfraction thing.
It might be interesting to understand the extension to that.
This is also along Gordon's line of just trying to understand the asymmetric case from the get-go, because that could improve the annihilations in the early universe. You don't have those if it's asymmetric. So.
Have you thought about doing this thing hyper with IR freezing?
So the difficulty, what's the difficulty with IR freezing? Let me think. So it's not necessarily a difficulty, it's just that you need to have a sufficient separation between when you stop doing the relic abundance and when your phase transition is. That's really the only condition, I think.
Well, I mean, as I said in terms of T reheat, I think the maybe more comprehensive way of dealing with the relic density and all the constraint is that you view the relic density story, including not only production from the freeze-in, but also afterward processing, like extra plasma decay production, of further suppression by the light annihilation and so on. So that will overall, if you think that way, will provide for A, richer physics, but B, also it's important to take that into account. And anyway, so yeah, please finish. I'm sorry.
No. Yeah, I'm just listening. Yeah, actually, sorry, I was thinking for the IR freezing case. So the one thing about the IR freezing case is that then your couplings are going to intrinsically have to be smaller, right? So the way that we went with the UV freeze-in is the initial mass is the big thing.
Yeah.
That's making the yield correct.
Right.
And making the processes sufficiently slow.
Yeah.
In the IR freeze-in, it's the couplings that are small.
Yeah.
And so then you kill your cross-section potentially.
Yeah, so the reason why I asked the question is, of course, one of the big question in the freeze-in dark matter in general is that, okay, it's great production mechanism, it's well motivated and so on, but it's hard to see.
Well, for the electrons, it's not. It's good for the electrons.
Well, only if you have a light mediator and you have a kinematic bump.
No, even in the heavy mediator regime. So if you look at Sensei, they're probing interesting parameter space both in the light mediator case and in the heavy mediator case.
So like, okay, what's the mass of dark matter in that case? Do you remember?
So it's above electron mass and then up to, I don't know, 20s of MeV or something.
Okay, so you have to vary the dark matter mass. Okay, right? For fixed dark matter mass, I guess you cannot do, I guess, either like heavy mediator versus light mediator.
No, you can.
You can?
In those Sensei plots, they're only ever sensitive to heavier than electron mass and not terribly heavy. So certainly sub-GeV. In that mass range of dark matter, there is both a heavy mediator and a light mediator freezing curve that they're shooting for.
Okay.
They're two separate curves. So actually the freezing story is compelling for the electron case especially because you can just get to it. But for coupling only to nucleons, it's abysmal. The cross section is 10 to the minus 53 centimeters squared or something. And so, yeah, that's why we're trying to play games.
Okay.
No, but the electron case is a lot better.
Yeah, okay.
That's why we started with this one, because there's so much less stuff.
All right.
Awesome.
Yeah.
Yes, let's thank
Yeah.
Rob again.
All right, good.
And then we have lots more time to follow up with many further questions.